We have minus now.
Все это чекай. Начало на... Не, пока не надо.
Should I come to Sergey? Maybe he will take me. We meet the director. I understand. Yes.
Okay.
Okay. So now 9:30, 10, something like this. He will come from my flat. Okay.
There was one more guy to come, I don't see him. У вас еще команда работает. Все готово?
Да еще начинать будет?
Да. Ну, давайте так. 2-3 минуты еще и начнем. До 3 минут. Так, Сереж, кто-то собирался прийти со стороны.
Сегодня, да. В России. Пятых поколений в России.
Садитесь, пожалуйста. Уважаемые коллеги, начинаем. Все готово, да?
Сейчас.
with engagement with a canon, is my pleasure to announce opening of the season 2024 of the scientific seminar of Interpretation Cosmology of the RUDN University. It is a great pleasure to see them here, Professor Dokladchik, the Vice President of the Russian Gravitational Society and the editor-in-chief of the Journal Gravitational Cosmology, and fruitful and successful author of original and very promising physical theories. I'm also happy to see at the seminar our talented researchers, Professor Dokladchik, Professor Kembridge, Professor Kembrидge, who is the colleague in the scientific agenda of our institute. And greetings to other our colleagues, teachers and students, and guests from other organizations, and also those who present here in the of the enjoyment. I would like to say that today we are all participants of a unique event. You must know that our university, and in particular the Institute of Gravitational Cosmology, has good contacts with the International Research Society. In our case, this is the case of physics. So I bear in mind that in this work we see outstanding physicists among them, Vincenzo de Sabata, Portugal born, and Roger Penrose, who recently won the Nobel Prize. Today we welcome a talented and already very famous researcher, the RUDN University professor, Spiros Cotsakis, with his German wife. From these items. Not enumerating his publications or theories, he suggested I only tell you that the British Academy of Science, the London Royal Society, has invited him to be the editor and the author of a special issue of the world's oldest scientific journal, Philosophical Transactions of the Royal Society. And this was a real recognition of Professor Cotsakis' scientific level. He kindly invited me to join as the editor of the field transfer, and a year and a half ago, 2 volumes of the journal devoted to future mathematical cosmology, containing 20 frontline research articles on the best world theoreticians, were published. I'm happy to remind that there were 6 papers written by colleagues from our institute. So I represent Professor Cotsakis and his presentation, the gravitational bifurcation for the Big Bang and black holes. Please, about 1 hour and maybe plus 10-15 minutes. And traditionally, to our seminar, we do not interrupt the lecturer. All questions and opinions after the presentation is finished, okay? Thank you very much. And I say in Russian a couple of words, excuse me. Коллеги, слушаем доклад без перерывов, не прерывая докладчика. Доклад час примерно, час 10-15 минут. И все мнения и вопросы и высказывания после доклада. Спасибо. Профессор Котсакис, you're welcome.
Okay, thank you, Alexander, for your kind words. I have the great pleasure of being here and the great honor of talking to this audience. Today, this talk will be about some very recent results that I have been working on the past year or so. I mean, the main subject of this talk and the results that I will show you maybe shape a new interface between general relativity and bifurcation theory, which is a part of mathematics, of course. In particular, I will talk about the interface between bifurcation theory and space-time singularities, especially the singularity theorems of Hawking and Penrose. I will explain more. You will see that... no, sorry. What did I do? Sorry, okay. Everything I will say is contained in the first paper here, which is already published, and the two other papers I have included in this list give you other problems related to this same approach of singularity and bifurcation theory. But I will mainly focus on the first one, on the results of this paper. Unfortunately, also, I believe that the real beauty, if there is any, in this work lies in the proofs and the theorems, which unfortunately I will not be able to give you any, perhaps very little of these proofs. Okay, so now this is the basic schedule of this talk. I will start by a very brief introduction to the general field of mathematical field of bifurcation theory, singularities and catastrophes. I will not say anything about catastrophes. Is an equivalent way of talking about bifurcations. But I will briefly discuss this, and I will use mainly and most commonly the word bifurcation to describe all three: bifurcations, singularities, and catastrophes. So it's a bit degenerate use, but anyway, it doesn't make much difference. And the next part, I will talk about the singularity, the well-known singularity theorem, problem in general relativity. And in particular, I will show that this singularity problem that we all know is in fact equivalent, can be phrased equivalently by necessity as a bifurcation problem. This is a very important observation, and I will talk about this. And of course, then I will give you some motivation as to why bifurcation theory may help to give some new perspective on the old results of Hawking and Penrose on this respect. What I will emphasize mainly is these two kinds of bifurcations that occur in this problem, the singularity problem, and then I will talk about how to use how to describe the metamorphosis of, as we say, of space-time singularities and black holes using the previous results. Now, as an example, I will give in some detail, treat the old problem of Oppenheimer and Snyder black hole, the original 1939 paper of them, and at the end I will give you some open problems related to these results. Okay, now before I start, I would just like to give you this quotation by a French, Henri Michaud, which is particularly relevant here. I mean, I Google translated this quotation. Now, I discovered this quotation a couple of days ago as I was finishing the slides of this talk, and I find it particularly interesting because it relates to perhaps the most important idea of bifurcation theory, which is the versal unfolding. Okay, so this guy here says what he says, and at the end he says that when there is nothing to unfold, then this is the state that the system lives, or maybe, he says he dies, but of course we can say he lives all his life. Okay, so I will come back to this quotation later on, just to see how interesting it is. Okay, now let me start with this part now. Now, of course, I will give some general remarks about bifurcation theory, and then I will describe very briefly the structure of bifurcation theory. That is the passage of how when you start from a physical system given by some system of nonlinear equations, you can use this theory to end up with the structure of this system. Okay, now I've given here three figures that played a very, very important role in bifurcation theory. Of course, Henri Poincaré was related to he's the originator of the word bifurcation and the first results. Of course, Vladimir Arnold is probably the guy who contributed the most in singularity theory. I'm talking about singularity theory of functions, not space-time singularity, just different subject. And René Thom, the French topologist René Thom, who introduced the idea, the theory of catastrophes. Of course, I think it is fair to say that in this field, Russian mathematicians have played a pivotal role, and it is not an exaggeration to say that most of the results that are known in singularity theory were done by Arnold, mainly by Arnold and his students. Well, now, of course, his students are not his students anymore. It's been many years since Arnold died, and but I think many of his students are still active in this field. Of course, there are other people who played a major role, like Andronov, who has also one of the most famous bifurcations by his name, and many other people. Okay, now let me. Sorry, what did I do? Okay. Okay, let me start very quickly with this general introduction to bifurcation theory. Now, what is a bifurcation? Now, many people, when they hear bifurcation theory, they have in mind that it's some esoteric, peripheral corner field that plays some minor role in physics, okay? Because it's not very, and of course in general relativity and gravitation is not used maybe at all. However, this is very far from the truth. Okay, let me just say a very few words about this. There are many ways to describe what a bifurcation is. One way is to say that simply that it is a mechanism by which a physical system gets transfigured, changes its form into something else. Its solutions of the set of nonlinear equations that describe the system change in number and in nature, and also the phase porters, that is the global dynamics of the system, also undergo changes. Now, bifurcation theory is a set of techniques that describes precisely how this change, the transfiguration or metamorphosis, or what Arnold used to say, perestroika, happens. And this, of course, is a very detailed and deep theory that, of course, I don't have any time to describe now. Actually, there are two ways that this bifurcation theory enters the game. The first one is if you have a system that contains parameters, but of course this is not necessary. In fact, if you have a system that has no parameters, bifurcation theory enters even in a more important way, in the sense of what is called imperfection bifurcation. Now, this is, I will come back to this, because this is the case where it occurs in gravitation, in particular in perestroika. Okay. Now, I have listed here some of the simplest types of bifurcations, and we have the Southern mode, which is related to changes of the system of the form that steady station of the system can be created or destroyed. This process effect, I will come back to this later on. The transcriptal bifurcation is what it says here. This does not appear in space-time singularities analysis. The pitchfork, which is the most important one of all, and it relates in other contexts to first and second order phase transitions. This is also called the cusp, in distinction to the Southern mode, which is also called the fold. And then we have the last one is the Hopf, the Andronov-Hopf bifurcation, which describes the creation or destruction of a limit cycle. That is a periodic orbit. Now, of course, we know that the linear systems can also have periodic orbits. The difference is that in non-linear cases, the limit cycle is a unique periodic orbit. Whereas in linear systems, of course, if you have one, you have an infinite number of them. Now, this also occurs, and we see how it enters in the discussion of black holes and singularities. Now, there are different kinds here of Hopf bifurcation. I'm not going to discuss now, but only when it comes to context. Now, some other points about bifurcations is that more complicated types of changes, these transfigurations of systems, can be described as some kind of superpositions, in quotation marks, of these simple ones. Another very important thing is the idea of codimension, which means the number of parameters eventually needed to describe the degree of complexity of the system. Now, you can imagine, of course, that in general we start with an ideal situation where we have a system, a physical system, that, of course, we need to perturb in order to have a more realistic situation. Bifurcation theory provides a way to tell you exactly how to perturb and what it means to perturb, and of course, how many parameters, that is, what is the degree of complexity that is allowed given the structure of the original system to the final perturbation. Now, we have another thing is that in the final picture of the final evolution of the system after bifurcation theory has been applied, there are some so-called bifurcation sets that are those sets in parameter space, I will explain, where all these changes happen to the system. This of course, very important and observable. Now, before I begin, let me also say something else. One might say very simply that there are two kinds of dynamical systems, either ODEs or PDEs, doesn't matter. Those that have the property that their linear part has only non-zero eigenvalues. I mean, the linearized Jacobian has non-zero eigenvalues. These are the so-called hyperbolic systems. And in that case, it means that the behavior of the given non-linear system is exactly given by that of its linear part. These systems, the hyperbolic ones, are not really important, and in fact, one might say that such systems, although non-linear, they are not genuine non-linear systems, because of course they are described by their linear part fully. However, there is another case, the case where in the linear part of some non-linear system there appear some zero eigenvalues. Now, this is the case of a degenerate system. Now, or singular. Arnold uses the word singular or degenerate. Now, these are the truly non-linear systems, because in those cases, their behavior is not described, of course, by their linear part. It means that if you perturb the system slightly, a nearby system may have completely different behavior from the given one, which is not the case in the case of structurally stable hyperbolic systems. I'm using some terminology which you may have heard but not very familiar with. Structural stability is a well-known idea in dynamical systems. It means generic or typical behavior, and I will come back to this thing. Last, let me say that if you embrace, so to speak, the singular part of a vector field, that is of a differential equation, then you're beginning to see what remains to be done. Now, I would like to say very few words about this space of structurally unstable systems. Just let me draw one diagram here. Oops. Okay, this is the Poincaré-Arnold picture of structural stability. Now, suppose that we have some kind of system here. Okay, so suppose that we have a three-dimensional space where it's the space of all dynamical systems. Outside here we have the structurally stable systems, and there are some walls of codimension 1, surfaces of codimension 1 that contain the degenerate systems. So we know that if you take here one degenerate system, you can perturb, and this system will go out and become, of course, structurally stable system. Now, the thing is this. By this situation, one might say that structurally unstable systems, degenerate systems, are unimportant, because if you slightly perturb, they become structurally stable. So we should only study structurally stable systems. In fact, this was back in the 60s and the 70s the main approach to dynamics. However, this is not true, as Poincaré and also Arnold have shown, because of the following thing. Suppose that instead of one system, you consider a family, one-dimensional family of systems like that, where for some, say this family depends on one parameter, and for some particular value of this parameter, you get this particular degenerate system. Now, suppose that you perturb the family. If you perturb the family, like that, then you get this other family, the perturbed family, where you see now that the degenerate system has moved to another point on the perturbation. So if you have one system degenerate, you can eliminate it by a simple perturbation. But if you have a family where for some value of the parameter there is one degenerate system, then if you perturb the family, you can never eliminate. So in fact, this example of Arnold shows that families of degenerate systems, if you have a family of degenerate systems, you can never eliminate the degeneracy. So the whole thing is, the whole idea is how to perturb so that the degeneracy remains. So it does not artificially removed by the perturbation. Okay, let me move on, because I think I'm behind. Okay, now I'm giving you here the four main stages of bifurcation theory, which are the following. Suppose that you start by a given system, physical system, that is defined by some system of nonlinear equations. What bifurcation and singularity theory does is to study this system, is to introduce a sequence of stages where starting from the initial system, you introduce other systems and eventually find what is called the versal unfolding, which is a new family of systems started from the original one, in which contains the set of all stable perturbations of the original system, in this way here. Then you use this versal unfolding and to construct the so-called bifurcation diagram, which contains two parts, the so-called parameter diagram plus the phase portraits. Now, I will give you examples of this, so I'm not going to spend any time of this kind of thing. The end result is that if you start with a degenerate nonlinear system and perform the situation described by singularity bifurcation theory, you end up with something completely different from that is traditionally described in nonlinear dynamics without taking into account this kind of thing. Now, in this kind of situation, there are other ideas that play a very major role: moduli parameters, symmetries, and of course there is some parallel field catastrophe theory that describes exactly the nature of the bifurcation sets using some other terminology, which I'm not going to discuss. It doesn't matter. Maybe I could respond to some question about this. Okay, let me now move on to the second, to the next aspect of this talk, which is the singularity problem. Of course, this I will describe this in two stages. The first stage is to give you a very brief account of the standard argument, as I call it, and then show you how we can reach a bifurcation program for the Hawking-Penrose basically approach. Okay, now okay, this is some notation. I'm going directly to the equations, and if you need something, I will return. Okay, these are the very well-known sets of equations. This is called the Newman-Penrose equation system of equations. This is the convergent. So we start. Let me tell you. We start with the convergence of causal geodesics. This is the standard thing. Now, of course, this is the two basic functions is the expansion of the convergence, or this one, the minus theta, the rho, which is called the convergence. And then we have this very basic relation between the expansion and the area or volume in case of time-like geodesic congruences. And this satisfies these equations here. The first step is this first system here is the one that is used in the Hawking-Penrose singularity theorems, and the second one is what I call the convergence vorticity system that takes into account the rotation of the congruence. Now, this of course is also discussed in the singularity theorems, but it's not it doesn't play much role in that. The whole meat of the problem is this system here. Okay. Now, these R and W terms are of course the usual contractions. This is the standard contraction of the rich curve. So this is the standard contraction of the Y, and then we have these systems. Now, I need to keep this slide over there as I continue. Now, okay. Now, once the main thing starts to show is, once you have a system like this, okay, here we have a two-dimensional system for rho and sigma. Sigma is the shear, okay, and omega is the tension, yes. Now, of course, the problem is this: how do we start the way an equation in the system interacts with the other equation? And the next question is, what is the relation of the genericity of the solutions of the system to the structural stability of the system itself? Now, Hawking and Penrose had a particular way to answer these two problems. And the way, of course, is very well known, and is described by the singularity. I've just written down here the statement of the singularity theorem. You know that we have this assumption, which is a generic condition, which means that there is no particular, in the null case, there is no particular alignment of the null frame with some component of the Riemann. Okay, so there is no degeneracy, so to speak, say. Then is the energy condition, of course, that everybody knows. And then there is the assumption of the trapped surface, which means that there is some time where there is a positive value of the convergence. Okay, you start standard. This is very standard. You start with a space-like hypersurface, and you assume that there is a two-dimensional surface in that three-dimensional hypersurface where rho has a positive value. Now, if these are the assumptions, then you know that you get one of these, they are all equivalent, either a focal point of the hypersurface or a pair of conjugate points where future geodesics refocus, or dynamically you have what is called a focusing state, which means that at zero volume the convergence or the expansion diverge. Then, of course, in any of these previous cases, we have a space-time singularity in general relativity according to the theorems in the form of geodesic incompleteness. Now, the way Hawking and Penrose proved, of course, this is that to take the energy condition and the positivity of that sigma square term, so that the first equation is called the Ray-Haldor equation in the system, becomes a weak inequality. Weak means that the equality is when these are both zero. And so, of course, by a simple integration that even a first-year student knows how to do, you get that rho, of course, diverges in a finite time. In a finite time and for some specific initial condition. So you have a focusing state that is space-time singularity. Now, of course, there is here the so-called Ray-Haldor effect. Penrose proved that by introducing this function over there, taking the second derivative, which is negative, and so the curve is concave downwards, and so you have the same result. Now, notice that the second equation in the system there, if the first one becomes independent of sigma, this second equation for positive W is a linear equation. So what they have done here is the Hawking-Penrose approach is this, that the Ray-Haldor equation decouples in a form of inequality, and the second equation becomes a linear equation. So they get what I say here, the feedback between the two equations is a linear feedback. Now, you can see this, I've written here in another way, it doesn't matter. I'm just going to show you the final result. You can get it in a different way using the Kronwall lemma to get exponential decay, which is the same, exactly the same, similar, equivalent way to get the focusing state as they did, but in a different way. The thing is this, that by doing what they did with the original system, they get the worst case scenario, which is this thing always acts to increase theta, the forcing term in the second equation, this rho sigma, the n, by the way, is 2 or 3, is a moduli coefficient, 2 or 3, 2 for null and 3 for time-like congruencies. So this equation, if you forget the W, the forcing term, which is the rho sigma product, acts always to maximize the expansion in the maximum. To drive the expansion in the maximum possible amount. So in this case, they get precisely, of course, the focusing effect. Now, in general, what's the problem with this? The problem is that, in general, if you have a system of any equations, like non-linear equations, x dot equal f of x, of course, f of x is a non-linear function, and the feedback, that is the dependence of one equation into another, the interaction between different equations in the system, depends on two things. First of all, on the initial condition that influences the solution, and secondly, the solution is influenced by the feedback term, by the forcing term. So in the system of Newman-Penrose Ray-Haldor, instead of the original system, Hawking and Penrose have, of course, this system here, the right-hand sides, where you see that the second equation has become linear. Now, of course, so instead of f of x, which is the non-linear forcing, they have a so to speak, linear forcing term. So it appears that the existence of a focusing state is a result of a linear feedback effect. So the conclusion I have here is this. Although the standard treatment of the NPR system provides only a linear feedback effect, and also the focusing state, there is a very basic issue involved here. What is the basic issue? Okay, the basic issue is that there is no linear part. If you see here, this system has no linear part. The linear part is the zero matrix. At zero, at the origin, if you get the Jacobian, there is no linear part. Okay, so you might say, so what's the problem with this? It's a very big problem in the sense that I will describe right now. Okay, let me very quickly tell you something about the meaning of the other condition in the singularity theorem, the generic condition. Now, we know, of course, from the standard papers, the pioneering papers of Penrose and Hawking, that when the generic condition is violated, that is when we have this, there is some, of course, unphysical situation. I mean, the space-time is Minkowski or some trivial thing. So no one wants to have this situation, of course, right? That is why Hawking and Penrose reintroduce these terms as non-zero in the original system. So that to have, I mean, generic effect. Okay, now the following observation made a very big impression on me when I first realized it. That when this thing holds, and of course in general relativity we know, as I just said, what it means, then dynamically, instead of this system, we get that system 7 over there. Now, this system is totally degenerate from the point of view of bifurcation theory, because the linear part of the system is a zero matrix, as I said. So it is a very interesting observation that when the generic condition is violated and fails, the system that we get is not some unimportant system dynamically, but is exactly what bifurcation theory calls a degenerate system. This plays a very major role. So the thing is that the non-generic condition of general relativity is equivalent to a degenerate system in bifurcation theory. Now, what I want to say, by the way, is that the work of Hawking and Penrose can in fact be recast in a bifurcation theory way. So what they did 60 years ago, almost 60 years ago, was actually to provide the norm. I mean, what they wanted to do is to give the normal form of the Reichenbach equation, and then using the energy condition to end up with the Reichenbach equation like that, where mu is the contraction of Ricci, which means eventually that when mu is 0, they have the degenerate equation. So for mu positive, this contained all possible perturbations of the mu equals 0 equation. This is what Penrose did. So with the inequality here and without these first two terms, the resulting inequality contains all possible perturbations. So if it contains all possible perturbations, then it means, using the linear feedback, that they of course get the focusing state. So the singularity, the space-time singularity in this sense is the only possible conclusion. Okay? Now, this of course is not the end of the story, because this system is of course does not have a linear feedback, but a hugely degenerate non-linear. So it's a problem par excellence in terms of singularity theory. Now, if you do that, then you have a list of questions, all of which are, I think, answered in my paper, about how to treat this system from the point of view of bifurcation theory completely full way. Okay, I'm not going to go through this. I want to show you what we get. Now, so if you start with the general system, when r equals w equals 0, and you follow the rules of bifurcation theory, so you start with this system, you find the normal form of this system, then you find the Bessel unfolding. So you end up with this one introduction of two parameters. I can tell you that my calculations from here to there is about 200 pages. Okay, so you end up with this, which is the Bessel unfolding of the normal Penrose equation. Now, from this one, of course, you can study the bifurcation diagram, and you can study the parameter diagram, the diagram of two parameters that describe all perturbations, and of course, end up with the final structure of all perturbations of the Newman-Penrose system. Now, what it means? So this gives you, by the way, the work of Hawking and Penrose, instead of this, just to compare, would be something like that. Sorry. So this is the positive. So this would be what they get instead of this. I will explain to you now very briefly what this is. Now these are this is the possible dynamical behavior of the Bessel unfolding I showed you before. So there are two axes, the mu1 and mu2 axis, and so at different points of this mu1, mu2 plane, at each point of this, you get a phase portrait. So this phase portrait is the rho sigma phase portrait of the system. Okay? So this phase portrait corresponds to the origin, where mu1 and mu2 equals 0. This phase portrait corresponds to the positive axis, that one to the negative, that one to this area here, this one to the one inside the parabola, and this one over there, and this one corresponds, which is the simplest, corresponds to the positive half space in parameter space. So it says the following thing: for any value where mu1 is positive, then the possible thing is that a runaway, so this is the rho sigma space, this is the runaway solutions that Hawking and Penrose have. So this is the rho diverging. So when you have, when you see diverging orbits, it means that you get a focusing state. So here you see, of course, a focusing state. Here you see a focusing state. The same here, the same there, the same here. By the way, these two lines here were discovered in John Stewart's book, Advanced General Relativity. Somewhere at the end, he says something, of course, we're using different methods, that there are, in the case where you have two parameters 0, you have these lines, these two lines here, without anything else. And so these two lines I call Stewart lines. These are, of course, separators of the flow. Okay. Very briefly, sorry, just to continue, of course, one can do the same with the rotation, the convergence rotation system, the vorticity perturbations, which of course play a role in the Hawking-Penrose analysis, but they cannot do here the same trick that they did with the with this system, because of this minus. Here is a plus, so they can use the positivity argument to get the weak inequality. But here, because of this minus, they cannot do it. So they just left the system completely intact. They didn't say anything. Okay, now of course you can do the bifurcation analysis of this system, many hundreds of pages, and you find this. Now, this is something completely different from the other one. the main feature of the bifurcation diagram of the vorticity bifurcations is not the focusing states, but the defocusing. So there are, I will explain later, but there are very few cases here where you have runaway solutions, like the one preferred by Hawking and Penrose, like the ones here. In the rotation bifurcations, you have, for instance, this very impressive phenomenon, which is a limit cycle, stable limit cycle. I will come back to this. Okay, let me continue to now give you some first glimpse into what this thing tells us about space-time singularities. Now, to continue, we have to give some physical interpretation in the parameters mu1 and mu2. It is obvious, well, not completely obvious, but now it is obvious that for the NPR system, one gives mu1 the role of the contraction of the Ricci, and the mu2 the full contraction of the Weyl. Now, for the other system with the rotation, we give to the mu1 parameter the same rotation of the Ricci, and to the other one, not rotation, sorry, contraction, and to the other one, I just take this to be a rotation parameter. This will help give us physical results. Okay, now here I of course write some what kinds of bifurcations you get from this. I mean, what kinds of changes in space-time singularities and black holes one can get by this diagram. The main thing is this. When mu1, that is R, is positive, the energy condition, we have attractive gravity and repulsive gravity. One very important thing that we see from the sub-node bifurcations that occur from here to here, this one is on the axis, to here, is that it connects a region of attractive gravity to one, I mean, it takes the system from a region of attractive gravity to one where the gravity is repulsive. So we find the result here that if you start with from a situation where you expect to develop a space-time singularity and you move the parameter mu1 from positive to 0 to negative, then you get de Sitter space. Okay, the same here, where you get anti-de Sitter. Now there is also a pair of pitchfork bifurcations through the parabola. Mind you, the parabola here means that R equal minus W squared over N squared. N is the moduli, okay? So this plays a very big role. So the system eventually, in quotation marks, ends up in this unstable, totally unstable SAD-like case where there are runaway solutions, but in the repulsive gravity case. Now, to continue, for the vorticity, one finds, for this particular case, similar, I've written there pitchfork and saddle node bifurcations, but the most amazing thing in this case is this Hopf bifurcation that one sees where mu1 is the R mu T nu, right? The energy condition positive. So here in the vorticity bifurcation system, one sees the formation where this is a rotation. This is negative. One sees the formation of a stable state, and I will come back to tell you what this might mean in the cosmological or black hole cases. Okay. Now, let me tell you a few things about this. First of all, for the previous system, for this one, which is the Penrose-Hawking situation, of course we get this. We can prove that we get this, which is exactly what Hawking and Penrose got. but only they got it only with mu1, that is the energy condition positive. So they got a focusing state. The other thing, however, that we get is the passage when a system starts from a singular state and moves to this one over here, then it has to continue bifurcate through the parabola to this kind of thing. Now, this is a shear bifurcation given by this, after center manifold reduction, by this equation governed by the shear, whereas this is governed by the rho. Okay, so what Hawking and Penrose have is the convergence. They only see at the convergence bifurcations. Here there's more, of course. Now let me say a very interesting little effect that is connected with this system here. This is the Gauss time. So suppose that you have this equation that we have in this case that corresponds to the Hawking-Penrose thing, and we can integrate, of course, trivially and find the time from minus infinity to plus infinity required for the whole bifurcation to be completed. Okay, this time, you see, there's a square root scaling law here. It's pi over root of mu1. Now, what does it mean? It means that when the system starts, say, the second space and we go back in time towards the singularity, there is a bifurcation here, so the system finds itself with positive mu1. If it finds itself towards the path with positive mu1 somewhere, then this says that the smaller mu1, the bigger the time it takes to the singularity. So when mu1 is very close to 0, epsilon to 0, then it means that this time is almost infinity. This is not an effect that found in the standard singularity theorems, because there, when you integrate this to find that at some rho naught you get the singularity, then there is no dependence on mu1 because they don't have any parameter. They just have only the initial condition. This is what I was telling you about the feedback. So here we have something extra, that the time to the singularity, if it exists, I will come back to this, depends on the parameter. The parameter here plays the role, the role of the contraction of the region. Okay. Now, I will come to something which I find really interesting. I will just spend 2 minutes on this, because I really need to move on to the hammer slide, and if I have 10 minutes or something. Now, this is of course a standard picture from Penrose's paper, primary paper, 1965 paper, that of course says this. I don't know to increase. Anyway, now this is the singularity here, as everybody knows. This is the black circle here is the flat surface. Okay, and then we consider the convergence of the characteristics towards the singularity. So once they start converging at the trapped surface, all the generators, ground in this case, they will eventually intersect. Okay? This is the standard thing. Now I have the proof here of Penrose's theorem. Forget about anything. The real essence of what he did is this. It is contained in this one. Now, what he does is a set of space-time pairs on large geodesics that start at the flat surface and proceed with an affine parameter all the way up to 2 over mod theta naught. Okay. Now, one shows that A is compact. Okay? So the set of all such points is compact. Now, the whole essence of this theorem is this. The existence of a focusing state, that is rho going to plus infinity, is used to show that every point on the boundary of the tau, of the trapped surface, the boundary of the future of tau, also belongs to A. Okay, so this it belongs because after this length there is a singularity, so it cannot proceed because theta goes to minus infinity there. So we see that the future, the boundary of the future of tau is a compact set. So, and because it is a compact set, it means that there is a singularity. Now, in our case, guys, the following happens. Put in the place of S the trapped surface. Now, we saw that here, when nu goes from positive to 0 to minus, this set, the boundary of the future of the trapped surface for positive there is transfigured to that at nu1 0 on the axis, at nu negative. Okay? Now, at nu negative, however, the compactness of this set does not follow. Why it does not follow? Because if you go from here to some negative, there are orbits like this one that do not have a singularity. So it means that not every point on this set with nu1 negative on the other side can be made to fit into the compact set. So Penrose's theorem does not hold. It means that in that case, the null geodesic generators, instead of refocusing, disperse into some other thing. Let me also, I will leave this, sorry. Yes, I will leave this. So this means that there are states where repulsive gravity, in this case, connected to the attractive gravity case, that are not focusing. Okay. Okay. Now, let me just finish by. I just need maybe 5 minutes. Let me just finish by going back to the paper of Oppenheimer and Snyder in 1939. That in a sense it started all. Because if you read the standard papers of Penrose, etc., of course, the whole problem from that time till the time of the singularity theorems was that the black hole disconnection and singularity at the center that they found, whether it is a general effect or whether it was just a result of the symmetry, this is spherical symmetry, exact. So the problem was whether this is just an effect due to symmetry or a generic effect. The singularity theorems, of course, say that it was a generic effect. Now, let me remind you, just to see what happens. This Oppenheimer-Snyder, this is Schwarzschild metric, of course. So I use, instead of their omega, because we use omega for the vorticity, I use an x here. The Oppenheimer-Snyder equation is this one. They solve, they find this kind of thing. This is the solution that they find, equation 27, I think, in their paper. So the R is this one. And so from this solution, which is a solution of this trivially, they find that, the standard Oppenheimer-Snyder result is that there is an optical disconnection with the exterior and the formation of the space-time singularity and the center in a finite time. This was their spectacular result. Okay, now let me just go quickly. Now, I can write this system, of course, this Oppenheimer-Snyder equation as a dynamical system. And of course, I can find a phase portrait of this system, very easy, a student can do. And of course, from this phase portrait, one sees that the coordinate x diverges to minus infinity. I mean, this goes like ln r. So it corresponding to the singularity diverges to minus infinity, and at outside to plus infinity. These are of course shown clearly from the phase portrait. Okay, now let us look at this system. This is not such an innocent and silly system as it looks. You know, if you find the linear part, it is this one. So it is not a zero matrix, of course, it's a semi-simple. 2 zero eigenvalues. Now this is called in mathematics that if one sees a system like this with f, the nonlinear part of Oppenheimer-Snyder, 0, and this one, y squared, being the nonlinear part, this says that one might expect what is called the Bogdanov-Takens bifurcation. This is a very, very complicated thing. Now, the most interesting thing of all, when I start doing this, the analysis of this system, the Oppenheimer-Snyder, is this theorem. Read the first one, that the second order term, the Oppenheimer-Snyder term, is non-resonant, it doesn't matter what it means, and it can be completely eliminated. The second order term in the Oppenheimer-Snyder equation plays no role. So, I mean, one ends up quickly to find the normal form, to third order terms, which is this one, and the versal unfolding. You can prove that the unfolding is versal. Okay, so this is, what did I do? Okay, so this is the versal unfolding. Now, if you continue for the, what did I do? Okay. This one. Okay. Okay, thank you. Okay, so okay. Now, this is the bifurcation diagrams corresponding to Oppenheimer-Snyder. Now, as you see in this equation, in the normal form, this is a plus minus, a very important plus minus here. This is called the positive and the negative moduli coefficient. This is what I call. And for the positive moduli, you have that thing. For the negative moduli, you have this one plus a part I don't show here, which is very complicated. It has global bifurcations, and I don't show. But already from this one sees that hidden in the Oppenheimer-Snyder model, you have two things. You have the unstable thing that Penrose found. The runaway trajectories that Penrose found, the singularity theorems. But in the negative moduli, you see something like the vorticity. So you see closed orbits in the Oppenheimer-Snyder system. Okay, so in fact, one can see, but if you look in my paper, you will see that there are various bifurcations. It's a very complicated problem, this one. There are various bifurcations associated with the Oppenheimer-Snyder system for the positive and the negative moduli, plus there is the existence of global bifurcation, which I don't show. Okay, let me now, by summarizing, so to speak, give you some open problems associated with this one. Now, the first one is, if you look at this one, which is, the mu2 axis is associated with the contraction of the vial, which is apparently energy in the form of gravitational radiation. Now, we see here that we predict effects, stable effects, occurring at W negative. So the sign of W, in fact, plays a role. Myself, I don't know what it means. Penrose assumes that silently assumes that W is positive. And if W is positive, that is what allows him to treat the shear equation as a linear equation, as I told you. Now, of course, if you let W be a parameter, of course it can be negative. Now, we predict phenomena that depend on the sign of W. What is the physical meaning of this sign? So, this energy. Secondly, there is a parabola here, mu1 equal minus mu2 squared over n squared. N is the 2 for null and 3 for time-like case. What is the meaning of this relation between the Ricci compression and the time? Now, something else, and I'm finishing. Let us take the bifurcation diagram for the vorticity. Now, and consider the case where we have cosmological case. What is in this diagram, we know of course that down here in the alpha stratum, there's a limit cycle. That is a closed orbit in the rho omega plane. Periodic orbit. Unique, stable. Now, what one can show is that this cycle always exists for any value of the parameters in the whole new plane. However, it becomes invisible when mu1 is negative. It becomes invisible. But it's never destroyed. So I guess in the cosmological case, this limit cycle might be expanding gradually. Okay? However, the most important thing is that, I think in my opinion, is that in the black hole case, if you consider the same situation for black hole case, of course, if the positive minimal always condition, we have the formation of this limit cycle, we have the theorems, we have Cotsakis forming, and so we can say that this, can we say that this limit cycle relates to the horizon? That's one thing. Secondly, in the repulsive case, where mu1 is negative here, so let me make sure, yes, here, there are no theories, there are no graph services, there is no energy condition, nothing. We don't have anything there. However, we do have this situation. Does it mean that cosmic censorship holds true eventually? Because here we will have negative singularities, of course. But we don't see why, because of this limit cycle, if it corresponds to horizon, it has become invisible. So I wouldn't say I expect, something more humble, that perhaps there is some invisible horizon, and in this way the cosmic sensor is what Penrose had imagined originally in the '69 paper where he introduced the cosmic sensor. So maybe the cosmic sensor is related somehow to this unique stable limit cycle that has become invisible in the case in the regions where we have no theorems and we might have negative singularities. Okay, now, yeah. So these are some further projects I'm working on. I have worked on, and I'm also working on now. I think I'll stop here because it becomes very complicated from here on. Thank you so much.
I will pray from here. No objections. Ladies and gentlemen, now please, first question, all the questions. Not necessarily just to say what you think about it. All the questions, please. You're welcome. I'm the first then. Spiros, is it possible, just in few words, to explain how the bifurcation theory, the mathematical part of the first part of your lecture, is connected, for instance, only for cosmological models? I understood of the Gödel situation, but what is the point of bifurcation? What is it? It is a part of just equations describe the model, or it is some, physical event.
Yes.
What is the difference? I'd like to know, but in few words.
Yes. Actually, you might say.
For simple people like me.
You might say bifurcation equals instability. So it is a way to describe how an unstable system, like a gravitational system, gravitational systems are unstable. That's the main characteristic. How an unstable system can go from one unstable state to another unstable state. If you see this one, or in fact the Hawking-Penrose bifurcation diagram, this describes all bifurcations. Okay, it means it describes all possible states of instability. Question: we see here that there is a singularity to be formed. Okay, in the form of focusing state. Okay, the question is, does it ever happen? So if you have the bifurcation diagram, that is the diagram prescribing all possible forms of instability that a system can offer, it means that this describes all stable perturbations of the system. So if it describes all possible stable perturbations, this system is stable. So in fact, the only thing that it can do, a system of which we know its bifurcation diagram, is to go like that all the time. It can never reach a singularity. So here we predict that rho will become plus infinity in some time, okay? But does it ever attain this? So the answer to your question is that bifurcations describe not the changes in one particular phase portrait, because here, of course, you see that if you take any phase portrait, you see that along some orbit, the system, of course, changes. But this is not a change in the system. This is a change given that the system is what it is. Here, you see change in the phase portrait. Is a one level up. It is a structural change of the system. So the system becomes something else. Here it does not become anything.
Well, in mechanics, we have just a very simple explanation. The stable system with its minimal of potential energy, for instance,
Yeah.
and maximum potential energy, unstable system. But what is here? How can you explain here?
Yes, here stability means structural stability. What is this? It means structural stability. It's another form of stability, which means that the system can go from unstable to unstable to unstable, but only those particular unstable states and nothing else. So in a sense, it is a stable family.
And due to parameters entering the equation.
Exactly.
Yeah, I understand, but these parameters are they in a way, response to the type of physical, physical conditions or physical points of physical interaction.
Yes.
What is physics there?
Yes. So of course, to perform this analysis, you don't. It's just symbols. You don't need any physical interpretation. But at the end, of course, we don't forget that we are dealing with a physical system. Now, the parameters have to correspond to some physical property of the system. For instance, in the Oppenheimer-Snyder system, the new one. So. In fact, spherical symmetric spacetimes are just at the origin. At any point different from the origin, any point would have in the parameter space two coordinates.
The deviation from spherical.
So what does it? One simple conclusion that we have from here is that collapse is a phenomenon that happens in any non-spherical symmetric spacetime rotational. So we expect collapse.
Yeah,
This is a small conclusion from this kind of analysis.
more or less clear. Please, Sergey.
Thank you for your very impressive talk and very detailed talk. It's a very non-trivial picture of bifurcation theory and its applications. My question is, could you please briefly explain the notion of versal unfolding?
Yes. Okay. Let me give you. Where to go? How to go from? Okay. Now, what the versal unfolding is? It is a family of systems. I mean, this kind of thing is the versal unfolding of this point. So a versal unfolding is a family of equations that describes all possible perturbations, acceptable, allowed perturbations of the original degenerate system. So if you have a system that is degenerate, how do you perturb it? You cannot just add at random some terms and say, okay, I perturb by adding cubic terms, or I perturb by adding some nth order term. Bifurcation theory tells you how many parameters you need for the full perturbation of a degenerate system, plus exactly which order of higher order terms comes into play. So a versal unfolding, you may think of it as a set of all possible perturbations, physical perturbations of a degenerate system. Now, most systems are in fact degenerate. They are not hyperbolic. If you have a system like some silly system with -1 and +1 eigenvalues, this of course is a stable system, so you cannot perturb. It's already there. If you perturb, you get back to, this is the notion of stability, structural stability. If you have a system that is structurally stable, any perturbation dies away. Just the system itself is already perturbed in some way. But if you have some degenerate, unstable system, you need to perturb. Now, you cannot just perturb arbitrarily, by adding whatever your physical intuition will give you to think, It's not like physics will tell us what to do. It will not tell us. We will think and decide. So, but this technique tells you exactly what is allowed from the mathematical structure of the system. Once you have the versal unfolding, once you have the set of all possible perturbations of any given system, then of course you can study that, the set of the perturbations. Now, what many people do without realizing it is that they don't consider physical equations once they have completed, they have found the versal unfolding. They consider the physical equations at the level of the original system. And of course, as Arnold has taught us, first you have to perturb the system correctly by asking the system itself how it should be perturbed, and then you have to find the dynamics. I think what the pioneering works of Penrose and Hawking for the singularity theorems have done exactly this. They have 60 years ago they thought of the bifurcation, but they thought only in some limited way. Not limited. They gave only what I showed you, only the runaway.
Just to justify all the first place.
this particular case, of course, we are okay. Let me take, for example,
Is it any one of these prediction which
yes. Let me tell you this one. Now, this system here describes the behavior of galaxies. Okay, suppose that n equals 3. If n equals 3, this system describes the long-term behavior of galaxies as points.
So by looking at these equations, you could make some predictions how it's for evolution of the galaxies.
Exactly. So you the one main prediction for this particular case is that if you follow the system in the past,
yes,
assuming that now is expanding the system of galaxies, there will be a time in the past that all galaxies will follow. Exactly.
As it is
This is the well-known prediction, but of course this prediction did not take into account some other features of.
This is what Penrose's original made.
Yes, precisely.
Your contribution, what you contributed here.
Well, I just said this. What he did was just to show only one. One second. Let me. Yes. So what we have found here. Penrose has solved this problem for mu1 positive, mu2 0, and so he considers only this axis. There is nothing else. So in this particular case, he says that if rho starts from the convergence of the congruence starts from some positive value, it will become infinite in a finite time.
Mm-hmm.
We did here the remaining cases.
For anti-gravity, all the stuff.
Yes. So because the W in Penrose is positive, but it's not even in that case. He does not consider the borderline cases and also the cases that lead from attractive gravity to repulsive gravity. So we see, for example, one prediction is this. In the case of repulsive gravity, there are also singularities. Any line here, solution curve, that branches off to infinity, it means that there is a singularity.
I see. What about the entropy in this case? Are all the galaxies evolution from the singularity to somewhere, or there are some clusters that could devolve back to singularity?
Both. Yeah.
So they could coexist.
Yes.
And so by looking at different
Yes. In fact, let me be more precise. As first Russians like Kalatnikov, Lifshitz, and Landau, even before, had said that we should not confuse the singularity, the congruence, than the real singularity in space-time. So what I'm talking here is a globalization of the argument of you have just a congruence singularity. Here we're talking about the possibility of real space-time singularities after globalization. I haven't discussed, of course, this, but it is assumed. Yeah.
Okay, thank you.
And of course, there is these other cases with the vorticity, the rotation that Penrose Hawking have not considered at all. Yeah.
Please. Some other questions? Please, Sergey.
As I understand, the singularities typically mean the incompleteness of geodesic incompleteness of manifolds. Maybe the bifurcation analysis provides some new criteria for geodesic incompleteness and singularity, structural singularities. Yes.
Well, you see, this is true. In fact, we see that I mean, the situation is much more complex than was originally thought, because we see that the role of vorticity. So there are vorticity bifurcations that lead to singularities here, for instance, where we have in this diagram, there are runaway solutions with this is the phase portrait of this region, the rho omega. By the way, you might wonder why I have drawn only the upper half of its diagram and not the full phase diagram. Of course, you know, this is a very important thing, because this system and sigma equal n rho sigma, say, this has the symmetry Z2 symmetry. So it means that this is something that is not actually considered in Penrose. This system of Penrose, this by the way are the optical Sachs equations, right? So these systems have Z2 symmetry, which means that you can only consider, if the sigma is the vertical axis, you can only consider only the upper half. That is why we have this, yeah.
Please, another question? No, I have one more.
Yeah. I was hoping, that you could help me with the sign of W, the energy.
The energy.
Yeah, anyway, we should maybe discuss it.
Okay. Do I correctly understand that the application theory is can be applied not only just to any non-linear theory,
Yes.
to any,
Yes.
not only relativity.
Yes,
so
yes.
on. And then from what you started this lecture, I have a feeling, I don't know exactly, a feeling. It is not the, to make the system linear from non-linear system, something like that. Just because you can change the, you can change variables. For instance, instead of rho, you can put a rho squared as a linear, and the system becomes linear in the variables which former they were not linear. Is it the way how the math of the bifurcation theory just comes?
Look. I think. I mean, of course, you may change. You
Technical questions.
may make whatever transformation you want to make. First of all, but of course, this does not mean that the transformations this will lead to physical systems equivalent. In fact, one of the most basic problems in singularity theory is the notion of equivalence. When do you say that two systems are equivalent?
Yeah.
This is a very important.
Right now.
Yes, exactly.
Because you can make this transformation.
Exactly.
But they are linear transformations.
Exactly. So and another thing is the standard. You have a system of differential equations which the linear part is hyperbolic. It has non-zero eigenvalues. Of course, we know from Hartman-Grobman theorem that this system behaves like the linear part. It means that the non-linear system and its linear part are equivalent. This notion of equivalence is very important. Yeah.
I see. Well, okay. More questions, ladies and gentlemen? Okay. Well, now please sit down. Sit there. Close to you, if possible.
Okay.
The most easy way to continue the seminar is finished because the questions. Now, declaration, please. Who would like to say several words? Okay. Because we must.
Very good thoughts or different ones.
You can say what you want. We live in a free country, the free people here. You're welcome to just to make a declaration or to say several words, please. You're welcome. Vladimir.
So, we have some activity in goes Bonnet and considers stability of solutions. And have a lot of questions also with Kubantai and other people. And we have some problem when this stability criteria needs some non-generacy one matrix to be
Generic.
yes,
Yes.
generic. Well, but the degenerate case was not considered by us. And also this is, takes place, for example, when there are subspaces, one-dimensional subspaces in our multidimensional. So maybe we may hope that your experience will help us.
Yes, yes, definitely. I will be very, very pleased.
It's really a question.
It's not a question, but you know, it gives me the opportunity to say something. I think, you know, I was very much impressed when I realized almost 3 years ago. You know, I was helping my son, who is a mathematician, to pass this course while he was still a student at university of differential equations dynamical systems. So we were talking about the case of linearization theorem. In fact, we were looking at the book of Arnold, the ordinary differential equations book, very well-known book. So he has, of course, the linearization theorem and says for which cases it is true, that is when all eigenvalues, there's no eigenvalues on the imaginary axis, I mean all eigenvalues are non-zero, so we have saddle nodes, etc., and focuses, and so that book that my son was studying from wrote that this holds for every system. So all systems in the book are equivalent to their linearization. So I read this, not Arnold's book, of course, that's the correct thing, but the Greek book he was using wrote this thing, that the linearization, essentially, you know, the linearization theory holds for any differential equation. Of course, this is wrong. So, this gave me the following thing. I said, while I was talking to my son, I say, but I haven't seen the other cases in any paper in gravitation. I mean, I had at home a very big collection of photocopies of papers of others, you know, but it just occurred to me back then that in no paper have I seen any other cases except those that appear in the linearization theory. So I went there and started looking in the papers just to see if I had it wrong. And of course, one paper says, of course, we don't treat the case where the eigenvalues are 0, one eigenvalue is 0, because this is not covered by the linearization theorem. The other paper says we ignore the 0 eigenvalue case. Blah, 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 blah. So then I realized that in fact, it was not considered. This is a truly amazing, I mean, it's a remarkable thing that in fact in gravitation, this problem was not considered before. I think most authors, so I think that it's worth trying to see what happens if you let the system behave naturally, you know? Yeah.
Please.
Well, I start very, very positively because he really demonstrated us a great mathematics, a great topic around, and he perfectly used this mathematical apparatus, how to say it, and very, very many things for this report. I even started to look differently on the singularity problem after this. At the same time, only just suggested only differential equations, from my point of view, are not enough to describe so complex problem as just bifurcation zone, it should be some integral relation as well to close the system of differential
Yeah.
equations.
Okay.
And you didn't talk about
No.
this at all, but still, in Russia, it was some polemic, and one of our theorists, Zubarev, or Anna Zabogalubov, who first realized that differential equations are not enough for complex systems. It should be
Yes.
caused by integral equations,
Yes, yes.
because there is conservation of energy,
Yes.
or even for structural changes, there is conservation of angular momentum, all this stuff.
Yes, yes.
And so, the nature exhibited the non-local
Yes.
character as well. The second quantum revolution. Therefore, we should rethink all this differential equation in terms of non-local harmonization of such complex
Yes, yes.
phenomena, like what should cause the system to restrict non-local organization,
Yes,
first of
yes.
all. So we should introduce time, coordinates, and show some internal degrees as a new variable.
Okay.
In the new variable in Liouville theorem, for
Okay,
example.
okay, I understand.
And after this, to use integral conservation for the new volume of multi-dimensional volume.
Yes.
To understand how it's all organized.
Okay.
If not, it will be complete. Maybe it's a great first step.
Yes.
It will give you an opportunity. And the other topic, all this analysis should, in some way, either to prove that the singularities are in physical reality or disprove. Because you talk very briefly that Einstein was wrong in 1938.
Thank you for.
39. But many people here in Russia, in Moscow at least, they believe Einstein was right at that time. Einstein at that time was right. There are no. You started from the dual model. There is particle and there is field in empty. But the ancient Greeks used another approach, Aristotle.
Yes.
The continuum matter, and quantum mechanics is all continuum matter. Monistic physics.
Yes.
It's very close to mentality of Greek people. Therefore, if Einstein told that there are no singularities because he proposed the non-dual physics without black holes that time. So your experience and your mathematical skills will give you the opportunity to model both approaches.
In fact, may I say something?
Yes, we are discussing.
What you say is very interesting for two reasons to me. I just want to tell you something first. I mean, I forgot to comment on this. I just wrote this for the following reason. You know, the paper of Einstein, of course, appeared the same year as the Oppenheimer-Snyder paper.
Yeah.
Now, I have read this paper, and to my mind, my poor mind, I have not found any mistake.
Absolutely, there are no mistakes.
Perhaps there are some mistakes, but I couldn't find. Now, in the book of Thorne, I think, Kip Thorne, the popular book, Time, what's the name? A popular book, a very interesting book by Kip Thorne, Twists of Time. Yes. There, I think he says that basically the paper of Einstein is wrong, and what is correct is the Oppenheimer-Snyder effect. So we expect to have singularities, and of course, I mean, the Oppenheimer-Snyder paper was the basis for the Hawking-Penrose analysis, and then everything became singular in the gravitational world. Now, of course, what I'm saying here is not that the Einstein paper is right, but all I'm saying is that the situation is not so clear-cut.
Absolutely. Absolutely, I agree.
This is
so you have a feeling.
This is the first point I want to make, what you said. The second one is what you said about continuity and discreteness. In fact, you know, the versal unfolding idea comes with something that is called the anteriority principle of Thom. So René Thom is called anteriority principle, which says, in fact, quite the opposite of the standard idea that quantum mechanics is the fundamental theory, and the continuum comes in some limit of quantum mechanics. This anteriority principle says that the continuum is the basic thing, so if you have a family, so the discreteness is some accident, because if you start with a family with a versal unfolding, then there is some value of the parameter that there is some degenerate singular system that we all try to understand. This is a discrete system, but the fundamental thing, according to this Thom, is the continuous system. So I mean, if you read these papers of René Thom's, he writes also about mathematics, how we learn about the integers and then we go to the real system, but the opposite should be true, etc. So there's a whole thing going on about how. So I think the versal unfolding idea has deeper roots than mathematical. It's a whole. I mean, of course, I don't pay any. I didn't discuss this at all. But definitely, it's not completely. I mean, proven mathematical theorem that the discrete is the fundamental and the continuum is an outcome of the discrete. In my opinion, it is not so.
Thank you.
Okay, great.
Thank you. More comments, gentlemen, ladies and gentlemen. No, I have one short comment. Please, slide number 42.
42. 1 second. This one.
Slide 42. Yeah. You see the Jacobi, the matrix 2 by 2 matrix, which has the Dirac determinant. Maybe not everyone knows that this is the unit of double numbers.
Yeah.
This is the unit of hypercomplex numbers here. If you square it, you get 0. But it is not 0.
Yes.
This is a so-called imaginary unit of double numbers. We know complex numbers, dual numbers, and dual numbers, not double. Double numbers and dual numbers. This is a dual unit. Its square is 0. And it is a hypercomplex representation. So, to some extent, it just makes me more excited, because the bifurcation theory in some way is interconnected with hypercomplex number mathematics. Okay. Everyone? More? No. Then we finish, okay? And we finish. No. And we finish, I said several words.
Okay.
No more than. It is a tradition. Okay. Even if I don't know very much about what to say. But when you started your really very interesting lecture, I sat over there and thought about, yesterday I told you about my short lecture, 1 hour lecture, in the Dirac seminar. 40 years ago, I spoke about the energy of gravitational field and tell about pseudotensors, many pseudotensors. And I just enumerate them and say this is better, this is better. And after my lecture was finished, Dirac was sitting on the first row, said, as a matter of fact, I never heard about that. Like me, when you started speaking about bifurcation theory, I'm very, very curious about it, and it turns out that it is, the good math, the good mathematics is mathematical reason you can use it and apply it. And the more I started understanding about it, there are some questions, but anyway, I think that when you
one example. This is the extension of the global universe. The extension of the global universe. What the universe because the fact that so but anyway, so I see the difference. The extension of the global universe. That's connected with that. I think that you understanding new sphere of investigation of gravity, especially when it wasn't the ground of the gravitation at all. And I understand that from the not only to GR, not only to Einstein's, but also some other explorer, so on, in cosmology, gravitational theory, everywhere. And if there are some bifurcations, then we can expect new models, we can expect new results, we can expect new predictions. And so I just, the only thing I'd like to say is just to wish you success in this new direction. So thank you very much, Professor. It's an honor to listen to your lecture. Thank you very much. Okay, ladies and gentlemen, our seminar comes to the end. Please, you are free to interconnect. And you excuse me, unfortunately, I have to go now. I know that Кирилл wanted to speak to you, so Сергей, я попрошу тогда побыть здесь, и кто куда поплыть, то, значит, там тем занимается. Договоритесь? Вот я сейчас буду говорить.
Okay.
Sorry. Thank you very much to everyone.
Thank you. Okay. Should I? Okay.
Сорни. Yes? Сор?
Tom.
Tom.
René Tom.
Principle. Okay, I will look at it.
Anterior. Yes, it's
It's interesting.
Yes.
But I have a question. Is in the Athens University people can be supported for the publication, like here? You know, RUDN is supported.
Yeah.
Is supporting his stuff, and what in Greece?
In some places it may happen. Yes.
Okay. But we are not sure about the Athens University. I remember also Atiner Institute. Atiner, do you know?